All right, welcome back to another mini lecture. So today I'm going to talk about boundaries and rules, right? And specifically, I want to talk about how good boundary conditions make good rules. That is, gives us conditions that tell us something about possible solutions to the wave equation. So I don't want to do the problem that's in your problem set, but I'm going to do one that's a little bit similar, right? So that I can give you the idea of how the algebra works out. So let's consider right now a string. And instead of that string going from 0 to L, let's let the string go from minus L to L. Now I know that this string is going to obey the wave equation, and therefore, and let me write the wave equation down as we want to say it, 1 over c squared, let's see here, d squared phi dt squared is equal to d squared phi dx squared. And I know that this is going to lead to solutions that look something like a e to the I omega t, e to the I kx. And I know that these solutions you can plug these into the wave equation to get the relationship between omega and k, which you all know is called the dispersion relation. Okay, so I think about these solutions, and I know that I can build up these solutions to give me some function, right? Some function of the string, which varies in both space and time. But now I'm going to use my boundaries, right? So I know in a lot of realistic systems, for example, like strings in a guitar, my string is not, the solution to the string is constrained because both ends of the string are tied physically to the guitar, right? And this is one set of this is one way to fix our ends, right? This is one way to fix our boundaries. There's another way that's commonly used where instead of causing the function itself to go to 0, I cause the derivative of the function to go to 0. And that's like having a little ring that's able to slide up and down a pole. But right now I just want to do one example, and so I'm going to consider this having both ends of this string fixed, which are also known as Dirichlet boundary conditions. Okay? So I have, because of this, two algebraic expressions, right? I know that the function evaluated at L at any time t is going to be 0, and that my function evaluated at minus L, again, at any time t is going to be 0, right? I have two algebraic expressions that tell me something about the ends. And like with all algebraic expressions, right, when I introduce new equations to a system, I'm almost always taking that system and I'm reducing the possible solution states, right? When I add equations to a system of linear equations, right, I'm then able to solve for more variables, right? Adding algebraic things are obviously going to restrict the solution space that I have. And the question is, how is that going to restrict the solution space? What is it going to do to all of my possible solutions? And for that, we're going to have to do just a little bit of algebra. So at all times, I know that the function has to be 0 on the right and the function has to be 0 on the left. So I might as well take t to equal 0, right? Because if I take t equals 0, my different solutions to the wave equation now, I don't have to worry about that e to the I omega t, right? I just have a e to the I kx. And then, of course, because for a given omega, k is either equal to omega or minus omega, so I'm going to add a second term, e to the minus I kx, right? This is just going to allow me to have both the right moving and left moving wave solutions for the same value of k. Okay, so now I want to evaluate this at my two different endpoints. I'm going to start by evaluating it at the endpoint where x is equal to minus L. And when I do that, I get phi of minus L 0 is equal to 0, of course, right? It's fixed on that end, is equal to a e to the minus I kl plus b e to the I kl. And if I do a little bit of algebra, what I find out is that must mean that a is equal to minus b e to the 2I kl. Okay, and now that looks interesting, right? There's some relationship between, in order for this to be a solution to the problem, I now see that there has to be some relationship between a and b. But I can also look at the other side, right? So phi x equals to L, which means phi of L0 is equal to 0, which is a e to the I kl plus b e to the minus I kl. And that gives me the fact that a is equal to minus b e to the minus 2I kl. And now it's like, oh no, right? How can both of these expressions be satisfied at the same time, right? If a is equal to minus b times e to the ikl, or 2 e to the ikl, then it seems very awkward that that it can also be equal to minus b times e to the minus 2 ikl, right? And of course, looking at this after a little while, the only way that these two things can possibly be true is if we somehow take advantage of or harness the fact that the exponentials are periodic functions, right? And therefore, if we choose the appropriate value of k, it might be possible for both of these things to be satisfied at the same time. So what happens is I could set them equal to each other, but basically I find out that e to the 2I kl has to be equal to e to the minus 2I kl, right? Which can only be satisfied, right, if for very particular values of IKL. How I like to do this is I like to take this expression, and let me put it on a new page. And I actually like to solve it for 1, right? So I'm going to say 1 is equal to, and I'm going to divide, I'm going to multiply both sides by e to the 2ikl, so I get e to the 4ikl. You're probably tired of me saying ikl. Anyway, if I look at the complex exponentials, I know that e to the I theta is only going to be equal to 1 when theta is equal to 0, or theta is equal to 2 pi, or theta is equal to 4 pi, right? It has to be some integer times 2 pi in order for me to get this thing to equal 1. And so I know that some integer, and I hesitate to call it I, so I won't. I'll call it n, okay? Some integer times 2 pi has to be equal to 4kl. Huh, it's beautiful. Okay, which means that k has to be equal to, right? Because now I really want to think about this in terms of k, has to be equal to L. N pi over 2L, right? And exactly what we found here is a quantization condition. I have found that k now has to be some integer multiple of pi over 2L. And just to show you how much you probably already knew this, if we remember that lambda, and so let me now say the nth lambda, so the nth wavelength, which is 2 pi over k. If I plug this in, let me see if I can do the algebra upside down here. So on the bottom, I have an n and a pi, an n and a pi, and the pi cancels the 2, the pi cancels the pi, and on the top I have 2. I have 4L over n. Right. And so what this tells me is that there are only a certain set of allowed wavelengths, right? There's only a certain set of allowed wavelengths where the lowest possible of these wavelengths, when n is equal to 1, right, is going to be given by 4L. Well, the string is 2L long, 4L being the wavelength. Well, that is, of course, just the fundamental harmonic of the string, or the first standing wave. And so you knew this, right? You knew that that I had a quantization condition on possible allowed values of the wavelength, but now we were able to actually get it from the wave solution. And so a good boundary condition gives us a good rule and allows us to quantize the possible values of k, which of course allow us to quantize the possible values of omega. More on that when we get to Fourier series.